Welcome back to the MCAT channel. My name is Patrick, and I will be your instructor for some structural organic chemistry. How's everybody doing tonight? So some of you guys logging in saying I missed the organic a little bit. Good. I had a good weekend. That sounds fantastic. So I know that organic chemistry can kind of carry some little bit of mixed feelings. There's some people out there that love it, which is great. There's some people out there that maybe didn't have the best time with it in their undergraduate courses. Am I right? Sometimes here or there you go through and you're like, I didn't really love it. I didn't really love the professor. I wasn't really too confident or whatever it may be. And either way, okay, if you loved it or maybe you blocked it out, it got a little too complicated, that's completely okay because the cool part about organic chemistry, especially going to MCAT 2015, is it's actually a really big opportunity to pick up quick, easy points. So the design and the way that we structure this channel session in particular is designed specifically to address any of the weak areas in your structural understanding of these molecules. But what do we mean by structural understanding? If you go back and you think about isomers, Lewis structures, Newman projections, and the like, what you're trying to ask yourself is, where are my weak areas? So I'll tell you guys, one of the best things that you can do as you go through this session is start a list, or simply just type a list as we go of the things that you feel like we go through, and like I might have to go back through that. Because as for all of our channel sessions, then you can go back to the archived recording and make sure to watch it a few times over, and boom, we have a nice efficient way to pick up maybe a missed concept that we had previously, and we just turned orgo into a strength. So think about this as your biggest areas of opportunity to really see improvement in this structural understanding of organic chemistry. So in this episode in particular, and like I say in all of my episodes, you got to think about why we're presenting the information the way that we do, because we want you as students to be able to pick up this information in the quickest and most time-efficient manner possible. So we're going to talk about representations of organic molecules. That'll be more of kind of a brief overview of what you guys have seen just from your base organic chemistry. As some professors like to say, organic chemistry, my friends, is a language, and it is just that. It's a language. So we have to make sure we understand the language of this structural representation. We'll also go through the different types of isomers, and we have a great chart that I think will make this information a little bit more digestible in the long run. And then lastly, we're going to go through that dreaded but ultimately great IUPAC nomenclature and give you guys some practice questions to really tailor it in. So let's jump in right away, get started, right in learning goal number one. How can we interpret the representations of these organic molecules? So you guys have seen them before. You can have things represented in different ways. So sometimes people like to ask, well, what's the point of having organic chemistry in the pre-med curriculum? Well, what it does, future doctors, is it kind of helps you understand going from 2D to 3D and back to 2D and really be able to manipulate that perceptual understanding of these molecules. So we start off here, you have your Lewis structures. That's probably going to be one of the most common ones we first see. You get into the wedge and the dash, right? Kind of preview a little bit forward. Is the wedge coming into the screen or going out of the screen? Is it into the screen or out of the screen? Get you guys warmed up here a little bit, right? Exactly. The wedge is coming out, right? Out back towards you, all right? The dash is going into the screen. Excellent job, guys. Then we have their Fisher projections we'll talk a little bit more about. And then the one that used to actually trick me up the most, I'll be honest, is Newman projections. I would look at those sometimes and be like, I think I need to see something here. So one of the caveats of this, of the MCAT in particular, you got to remember, you're not going to have a molecule with you or the model kit with you. So yeah, Navina, and I was the same way. I thought Newman was the hardest too. We have some really cool animations to show you guys tonight that I think might help you out. And maybe it won't be the hardest anymore, okay? So 3D projections, what's it all about? We need to be able to understand the physical representation of the spatial arrangement of these particular molecules. So we look at something like here, R2-chlorobutanol, okay? Well, I know that there's going to be chlorine there. I've taken that kind of the prefix. Butanol, methyl, ethyl, propyl, butyl. I'm counting to 4 there. So I got to have 4 carbons. And I know it's got to be in that R configuration. Okay. But what it means, and we want to get inside the minds of the test makers. I know, when you're thinking like, when I was little, I didn't grow up wanting to be an MCAT test writer. All right, when I was little, I wanted to be Batman. All right, I'm still trying to find the utility belt, but we'll get there. Now, R2-chlorobutanol, why do I say it that way? Because if you can think like the test writers, then you can start to understand they can show you 3D projection in a lot of different ways. So check it out. All right, it's unlikely that you're going to see the pure 3D projection like this, because it really is the most complete view. And you can see, you can rotate these things around by just simply clicking on the slides here. That's just like we have with our own model kit. So if you go back and think, all right, I can take this whole, look back at it for a second, 3D projection, I can put it in a Lewis structure projection. On the left and on the right, is that the same molecule? Yeah, absolutely. Now, why are we bringing it up or presenting it this way? Because think about it. I'm representing this molecule. That's what I want in my head being able to theoretically visualize. What we're showing on the left of the Lewis structures is how that's represented. Now, I'm always a big believer in keep it simple, right? Don't overcomplicate anything. So when we're looking at this, I always can say to myself, all right, I just have to make sure the dots and the sticks end up lining up, right? The dots being my lone electron pairs, the sticks being the bonds that we're forming with one double bond with this carbonyl group, carbon double bonded to my oxygen. Okay, that seems fair. So it's still R2-chlorobutanol. Now, let's take a look at a little bit different here. If we talk about Lewis structures more in depth, what am I showing you guys here on this slide? Just as a way of review. Resonance structures, right? So let's just do a quick recall, especially kind of set the scene for later on in this lesson. You guys got it. The greater the number of resonance structures, the greater the what do we generally say in organic? Boom, little MCAT magic here. It's all about that stability. So even though as we work through this, you guys can see these different areas, and now I'm going to change my marker color to red so you guys can see what I'm circling and kind of talking about. We have this positive sign here and this negative sign here. Those are areas of localized charge, right? So if I have that negative, is oxygen more electronegative than carbon? Sounds like a very simple question, right? Yeah, see? All right, now you guys are probably thinking, and I know that there's some of you out there that came to this session tonight being like, ugh, it's Sunday, I don't really even like Orgo, but I got to go to this, I got to see it. It's okay if that was you, all right? I'll let it go, because by the time we get to the end of it, you're going to be like, that wasn't so bad. I was just kind of reviewing stuff that we knew. Because think about it. If we understand our basic parts of electronegativity, we know where some of this electronic charge is going to start to go to. So if you see a carbonyl carbon and the oxygen is ultimately a little bit more negative, that's why we can write partially negative for the oxygen and partially positive for that carbonyl carbon. So I'm going to preview towards some of the other channel sessions you guys might go to. If you look at the carbonyl group as a whole, what is going to be a good electrophile, that carbon or that oxygen? See how easy this is once we kind of break down the basic gist of it? Absolutely, guys. This is it. This is nice and easy. This is quick points to pick up on testing now. You're absolutely right, the carbonyl carbon. So what we show here with this Lewis structures is ultimately this top one, that ends up being our hybrid structure of our resonance structures. So ultimately what happens is you do get movement of this general electron trends or conjugated systems throughout. But when in doubt, think to yourself, which individual molecule is more electronegative? That's where more of that electric density is going to get pulled to. So whenever you're in doubt, don't overthink it. Just stop and say to yourself, okay, I know that electronegativity is going to have hold over more of that electric charge. That'll give you a clue as to where that electric charge is going to be pulled towards. Okay? Excellent work here, guys. Now, all right, when we jump in, our next one that we're going to show here is our wedge and our dash projections. Okay? Now, if I show this one more time, if we have the wedge, and when I mean the wedge, but what I mean by that is this solid wedge here. Is that coming back towards you or is it going into the screen? Okay. And Laura, I see Justine typing out the answer to that question for you just so you have it. Good. It's towards us. It's coming back out towards us, right? The dash going into the screen. Now, this is a basic convention in our organic chemistry. We have to know this. This is the rules of the language. We need to know going into this. So when we see that, if that wedge is going out of the page and the dash is going into the page, every time you come across something like this, you know the general idea of what we're trying to three-dimensionally represent. If I see it, is this still the same molecule that I looked at previously? Well, yeah, right? The only thing we're doing is showing a different type of projection, but ultimately showing the same structure. Look how that moves. Now we're just looking at it from a bird's eye view, or from the top, from the way that we originally looked at it. This red right here, what is that representing? That's my oxygen, right? We mentioned this earlier. If we have that carbon-no-carbon, what we're showing you here, and I can circle this in red, that's just coming out of the page. That's what we were originally looking at. Let me know we can confirm the back on the top here. That was into the page. So what we're showing you guys is how this represents the dash going into the page, or into the screen, as we're looking at right now, and the wedge coming back out of the page. So the question that I want you guys to keep thinking of, why are we showing you guys this first in this channel session? Notice we're building towards our isomers, which we'll get to here shortly. Okay? Now, showing again, I know, this is like one of my, I gotta be really honest with you guys here, this is actually one of my favorite sessions to teach. I just kind of nerd out over the projection things, because I used to be really intimidated by orgo, I'll tell you guys that honestly, and I realized once you get to the MCAT, it's not as bad as we have it in our head. And that's really a cool thing when it comes to scoring quick, easy points. So, third one here, we show Fisher projections. Okay, with Fisher projections, and again, oop, what did I just do there? I look at this first. Now I'm going to rotate. Theoretically, is that still the same molecule? Absolutely. Good. We're just rotated. Mary, excellent point. We just rotated the molecule. It's still the same molecule, we're just being projected to us in a little bit different of a way. Okay? Now, as we see this, okay, think about it. What a Fisher projection is the way that it's presented. I always like to say that Mr. Fisher wore a bow tie, right? Mr. Fisher wore a bow tie. Because when you look at it, sometimes you guys will remember this back from your courses. If we look at something horizontally, sometimes people would write that out with the dashes, meaning it's coming out of the screen or out of the page, right? Well, if we look at that, I'm going to erase this now, and we compare it, my bromine group and my CH3 group are coming out compared to that Fisher projection. So the idea here is we want you guys to be able to visualize what's happening here. Excellent job. Now, let's go one step further with this. See what we did there? I'm going to go back one more time. I want you guys to see this. Notice the red lines. Okay? So you have OH right now coming back towards you, and H going into the screen. Absolutely. Okay? Now watch this. When we bring this up, we're just rotating that 90 degrees. One more time. Now we can see that same molecule. So theoretically, we're just showing in a Fisher projection this 3D representation. What we have to get comfortable with is when we look at it, how can we rotate it 90 degrees, flip it, invert it, or go all the way around? But what we're showing you guys here is that's really what makes this at first kind of confusing. But as soon as we see this visualization, boom, now I know what's being represented here, which is to now your advantage, right? How many of us had all of our organic chemistry tests when we were in undergrad multiple choice? Yeah, right? Probably very few of us. Now you think about the context of the format of the test. We go through our assess and plan steps. You guys actually have an advantage here because all of your answer choices on the MCAT is in multiple choice format. So if anything, this is also going to help us eliminate wrong answers, just giving us a statistical edge in the long run. Good. Excellent job, guys. So continue that rotation. So when we see this, now we're going to the fourth one with Newman projections. What is the advantage of having a Newman projection? Something that I think sometimes is lost in translation when we go through and first review it. But why do we have Newman projections? What does it show us? Yep, very good. That's the first thing. Steric strain. Steric hindrance, absolutely. Hindrance or strain, we can use those words interchangeably. And what it does, if you have a single bond, can you have rotation around that single bond? Crystal, there it is. Exactly. Exactly. If we can have rotation around those single bonds, Newman projections are actually to our advantage. Because think, if we go back here, you can rotate around this single carbon bond. So imagine, look at my screen right now, and if I have my hands, can I rotate my back hand there? And obviously you see my thumb in a different projection, right? If I rotate back again, my thumb is going to be over here on the same side. That's the only thing that we're really showing in Newman projections, is which way is it really going to be. Now, with that, there's going to be certain Newman projections that are more stable than others due to that steric hindrance or that steric strain. Think about it. If we go back and we gap this together, remember electrostatics? If you have two negative charges, think electron clouds, really close together, is that a good thing in terms of stability? No. But you guys already know that going into this. So if anything, that helps you kind of predict what's happening here. So if you have that steric hindrance, what does that do to the potential energy overall? Increase it or decrease it? Ooh, man, I cannot slide anything past you guys tonight. I love it. You guys did your homework this weekend. So what the Newman projection does, and you guys can see this is one of my favorite animations in this first part of the deck here. You can see the eyeball, right? That's our point of view. So what we're doing, see this happen. Uh-oh. What does that show? We're literally looking down that carbon-carbon bond, right? So what you see here, if you see this eyeball, notice if I'm looking back, my chlorine that was going into the page, that's that chlorine right now. You have that carbonyl group, but that oxygen is on the left. You're looking down that carbon-carbon single bond. Excellent. So if we continue to use this idea, you can visualize it any which way. But what we can also know, you guys will see this here in just a second, this is the Newman projection. So watch this. If we flip, what did we just rotate? I'm going to do it one more time so you guys can see this. These are my favorite parts. I'm totally going to nerd out on this, so you got to let me go with it, but check it out. Imagine if we had this in our undergrad courses, right? You see these kids playing on iPads now. I wish that, like when we took it, it was like all iPad everything, right? You'd be able to actually visualize this. Take apart your model kit, it's the same way. What we're doing is we're literally rotating around that carbon-carbon bond. Okay. Well, now as we start to see that rotation, these different conformations, ooh, buzzword right there, conformation versus configuration. Don't confuse those two. We'll get to that in just a second. Now we can start to see how this is actually being physically represented. Okay? So all the way around, and we're good to go. So let's look at a question like number 1 together. If you guys first got to this question on test day, would you look at it and be like, oh no, this is going to take me a long time, I got to skip it, right? On first glance, probably. Okay, Laura, you might say that at first, but wait just a moment. If I look at these 4 answer choices, of course we need to understand nomenclature. What it's asking us is which of the following incorrectly represents glycerol 3-phosphate in the S. Okay, Laura, you'll hate a lot less. Watch how awesome this is. This is our first little MCAT magic here tonight. What must be different in the correct answer? Okay, Mary, that's a great point. So Mary is the first one to say it, or Crystal too. So you guys are saying the same thing. You only have to pick one that's actually different, but either the molecular formula or the relative configuration. In any of these answer choices, does anyone notice something that actually kind of sticks out because it's the wrong number in terms of the molecular formula we're looking at? Anyone notice that? Carbon number. Ooh, Kathy, Mary, Emma, yeah. Check it out. If we look at this, and I go through all the other ones, how many carbons does A, B, and D have? A, B, and D has how many carbons? 3. How many carbons does answer choice C have? Okay. Well, wait a second. Is that even then representing glycerol 3-phosphate? Even if you forgot what glycerol 3-phosphate was or had no idea. No. I'm done. So, did I have to go through all that time going through answer choices A, B, and D to figure out my configuration? Heck no, I didn't. This is great. I just picked up a nice, quick answer choice in a really short amount of time. All right? Alexander, this is what it's all about. You actually learn to love the MCAT in the long run, because if I can pick apart answer choices like this, boom. All right? Nice, quick, easy point, but I'm going to build myself a little bit more time for a harder passage later on. That's the name of the game. Remember, in any of these things that we're looking at here, we want to be balancing speed and accuracy. You don't want to go so fast that we're making silly mistakes, but if we go through, exactly, that is what the name of the game is. Why are you guys here tonight? Want to get more points right on test day. That is exactly what we're focused on. So we're getting right into learning goal 2 because what we really just did with learning goal 1, it was just kind of a warm-up. What we want to see here is we want to recognize the differences between different types of isomers. This is what I'm talking about right here, guys. This is the part that I always recommend, especially after this session. Maybe on Monday or Tuesday, go back to the archived recording, check out this flow chart between the yes, no answer choices. So we're going to go through it tonight. Please go back through it a few more times. It's a fantastic way for you to then just kind of differentiate, diagnose as you go through what is what in terms of our isomers. So check it out. Isomer differentiation. What is an isomer? Isomer is two molecules with the same molecular formula. Something's different. So what I always tell people, and this is something that I did especially, there's 3 C words here, okay? And you're going to watch constitutional, configurational, conformational. It sounds weird and super wordy when I first say it, but watch. I'm going to highlight them as we go through. So we start. You ask yourself, are there the same number and types of bonds between the atoms? If we here say no, what we know that we have is a structural isomer. What do we sometimes also call structural isomers? So I'm gonna ask this. This is something I really want to make sure to make a point of. We have a structural isomer. What do we also call those? That's the constitutional isomers, okay? I just want to be very specific here because that's something that can get confusing if we see it on test day and we don't play on that certain word choice. So just be careful on that, okay? Constitutional. But you can see here, all of them have the same molecular formula of C3H6O, but what we see, okay, this is easy for us to be able to visualize on test day. If they don't have the same bonds between them, I know I'm going to be able to go through. I got propanone, propanol, propanol, right, aldehyde here, then I'm good, okay? So tons of different structural isomers when you really think about it overall. So these are a little bit easier to see. Now, let's get into more of the nitty-gritty here. So we started with, okay, what if I said yes to that question? Well, hold on. The same number and types of bonds between the atoms. This is the whole other side which we really focus in on. So we start here with stereoisomers. That's what really probably got the main focus in your undergrad class. This is where we go a little bit more in depth with the MCAT as well. So let's take a closer look. My next question in my differential diagnosis here, okay? Check it out. Compounds can be interconverted by rotating around a single bond. Let's say that we say yes. If we say yes, what kind of isomers are we getting to? Here's my next C. Think about it if you can rotate conformations, right? Watch this. If we get into this, this is our conformational isomer. Because if you can rotate around, remember I was showing you guys with my hands earlier? I can see 2 thumbs right here, right? So if you look directly at my camera now, how many thumbs do I have? Do you physically see right now? I only see 1. But if I rotate, right, or then I rotate the back one, how many do you see now? Okay, I can literally rotate then conformation. I had a TA show me that one time when I was a junior, and I was like, oh, that's so much easier to think. If I got 2 hands in front of me, I can rotate. That's the conformation of my hands. It allows you to remember the nomenclature of what's being asked. Okay, so conformational isomers, what can we visualize here? This, my friends, goes exactly back to what we were just talking about, our Newman projections. That's oftentimes the way that we represent it. So we showed the eyeball just like we did earlier, right? And I want to think, I'm looking down that carbon-carbon bond, and what we see, look at this. The beauty of the visualization, right? What are we looking down now? That same carbon-carbon bond we looked at in the previous slide. So now this starts to make sense. Let's go one step further with this, okay? I can see it any which way, but what I can also do is I can get the rotation in the back. This is where Newman projections are important in terms of our conformation of the rotation that we see. So remember when I was asking you guys the questions about potential energy and that steric hindrance or strain? This is where it comes back up. So notice we're just kind of building the pattern here, so it's all going to come together as one. Just wait, I love this part. So the bulkiest groups on the front and the back carbon, okay? Why do we think of it as the bulkiest groups? Because what we want to see is the movement, right? I don't want those big bulky things close. We said this earlier. If you think about electrostatics, if I have two electron clouds that are really close to one another, what does that do to my hindrance? Does it increase it or decrease it? Increase it. If you increase that steric hindrance, let's ask the follow-up question now. What does that do to potential energy? Exactly, you increase it. Very good, guys. See how easy this is? Now check this out. You look at the bulkiest groups here in the front carbon. So we start here with CH3 on that front carbon. The back carbon, you're going to get the chlorine. Now what we ideally want to do to keep stability is you'd want to probably have those as far apart as possible. So here's where stability comes into play. Ultimately, what a lot of our MCAT questions are going to focus on. If we have our bulkiest groups the farthest away, we call that staggered anti. Okay. Now, we go one step further with this. If I look at my energy, do you think this is going to have a little bit lower of an energy or a little bit higher compared to the other ones we're going to look at? Yeah, because if they're farthest apart, probably not going to have as much. But notice that's why I asked you guys that question 10 minutes ago. We're just setting the scene here. So if I look at this, this is my lowest point on the graph. Now this is cool because what we're going to do is we're going to show this whole graph here in a second. Now, let's go one step further. Ooh, what did I just do there? Tricky. I only changed it a little bit. Right? But I didn't change it that much. Right? Ah, Kathy took the words right out of my mouth. We're increasing energy. So check it out. This is what we call eclipsed. All right? Now everything is the same way. I'm kind of eclipsing it, right? What's an easy way to remember that? The eclipse position. When we talk about like a lunar eclipse, the sun and the moon, it's kind of the way I always think of it. Yeah, lunar eclipse. Mary, perfect. I think the same way. All right? Great minds think alike. Okay? So if you see that and it covers it up, you have that eclipse conformation. Notice I continue to use the word conformation. We'll get to configuration here shortly. Now, that's going to be a result in a little bit higher of an energy. Is that technically my highest potential energy position? Not yet. Oh, I love, man, you guys are on fire today. I love it. Okay. Now, wait a second. What did I do? Go back one more time. Check it out. I rotated one more time. Right? Okay. Well, if I rotated one more time, what I'm doing, that's gauche. Okay? What does gauche mean? What does the word mean? I think it's gauche, actually. Yeah, it's left in French, for those of you guys who took French, right? So what it does is it comes from the Latin, which means awkward. It's a little bit too close together because it's next to. It's awkward that those groups are too close to one another. So while it might not be as high in potential energy, all right, it's really not the most stable. So it's kind of this in-between awkward thing, and you're like, what's going on here? All right? Now, watch. Be very careful here. When we see this next rotation, notice where we're going to go on the graph. Okay? Watch closely. What do we see? It's weird, but what do you see? All right. Now we just got to higher energy because what we did, the bulkiest groups are now overlapping. Excellent. See, if we physically see this now, you're going to be able to visualize this and recall it later on. So just by noticing this rotation, if you think of my thumbs as like the bulkiest groups, that was the first one that I showed you guys, right? So if I have both thumbs right next to each other, whoa, that is super bulky. But what it's also going to do, that's my totally eclipsed conformation. That, my friends, is going to be the highest potential energy that we're going to get. Now, we could rotate one more time, right? Now, that's not as bad, right? But that's still gauche. I still don't like, it's staggered, but it's not perfect. It's not going to be the lowest amount of energy that we have. Now notice, we're almost all the way around the circle. We keep rotating, we keep rotating, we keep rotating. Okay? So I saw a couple great questions in here. If you think about it, I rotate it one more time, then what I just got back to is my eclipsed. But the Volkius groups aren't necessarily the closest together, so it can't be my highest potential energy. When I finally get all the way back around, look what I see here. Okay. Think about it. If you look at this, which conformation ends up giving us the most stable conformation? Right here, our staggered anti. Very good, guys, because our bulkiest groups are far apart as possible, right? We said the chlorine and the C3 or the CH3 group. Now let me go back. Which one was the least stable overall with the highest potential energy? Okay. Yeah, anti would automatically be staggered, Kapte. Yeah, you can think of it that way. And then good, the totally eclipsed, right? Because that totally eclipsed, we have them literally right next to each other. So if you have that, now what does this allow you guys to do as test takers? Remember, I always want to bring this back to test day because we're trying to score more points correct. What does that bring us back to? How can we use this to our advantage during the test? Well, obviously, we're going to be asked to get higher scores. Well, think about your strategy, though. Can't I use this as a way to eliminate answer choices? Theoretically, right? Yeah, absolutely. And Felicia, that is a great point. So let's combo that. That's kind of our 1-2 punch here. Because theoretically what I can do, if I can eliminate answer choices based upon this, then I can say to myself, yeah, if I'm looking at staggered versus eclipsed, those help me remember, because I'm looking at Newman projections, that these are conformational isomers. So watch this. Now, if we go back and we go one step further with this, we're going to look at cyclic ones and then compare and contrast this to configurational, which will help us kind of separate the two in our mind. So cyclic ones, you don't necessarily want super tight cyclic rings because they're not what? Sounds like a goofy question for me to ask, but I always bring it back up. Yeah, now you guys are getting the theme. It's the same theme over and over and over again. So check it out. If I have cyclobutane, methyl, ethyl, propyl, butyl, that's only 4. I'm not loving that yet, right? There's a lot of steric hindrance in there. We call that puckered. Now, if I get to, okay, I got 5, methyl, ethyl, propyl, butyl, pentyl, is that going to be a little bit more stable? Maybe a little bit? Yeah, a little bit. But ultimately what I want to do, that envelope structure, that's still not as nice, exactly, as me getting to my chair or boat with a cyclohexane, hex meaning 6. So that boat or that chair conformation, let's check this out. We're going to look a little bit more in depth in the cyclohexane conformation, but what we know is that if you increase the ring strain, starting with that cyclobutane or cyclopentane, what that ultimately has then, that's our highest area of instability. So as we get more or closer to this cyclohexane chair conformation, you have increasing stability, because ultimately what you're doing, just like we looked at 20 minutes ago, is you're decreasing the ring strain or that steric hindrance overall. Good. Excellent. Now let's take a closer look. We're still in conformational isomers here, right? So if I look at this, I have 3-chlorocyclohexanol. Okay, well 3-chloro, I have the chlorine on my 3rd carbon. Hexanol, that OH group, giving it the OL at the end. I have a nice representation here. Now, we have something called axial versus equatorial. Axial substituents are less stable than equatorial. How do we know this to be true? Watch the visualization here. If we flip this now, we put our chlorine and our OH into equatorial. Now wait a second. Which one has those substituents farther apart? The equatorial or the axial? Exactly, the equatorial. So when we have the axial substituents and we flip it over, that flagpole strain causes the ring flip. What we mean by flagpole strain, if you guys ever hear people say that as slang, they're both pointing up. Every time you look at that 3D representation, the flagpole strain shows that those two groups are closer together. So what we're going to do is we're going to go through a conformation flip to get 3-chlorocyclohexanol again, but in a better way. So equatorial substituents are more stable than axial. Now, Mary, you just brought up a great question. I was just about to go there. When you flip the ring, that automatically switches axial versus equatorial. You are 100% correct. That's the key to it, because what the ring is ultimately doing is just increasing the stability overall. We're not done yet, though. Check this out. So if you think about it, we're showing a 3D representation here. Now, wait a second. Okay, let me go back. Check that out. Aren't we looking at this kind of from a bird's eye view then? I'm looking down on the molecule. Does that make sense? I'm looking down on it. So imagine if you had your model kit right now, just to kind of give yourself visualization. It's kind of weird, it is, but you're looking down on it. Now watch me flip this. Okay, if you look at it, all of the red are axial. They literally line up on that vertical plane. So if you have them on that vertical plane, ooh, that gives me a big clue because it shows how they're a little bit close together. The blue are the equatorial. We're in the chair position. Now watch this. This is the most important part. If you up and down groups alternate between the axial and equatorial, right? Check it out. If you have this, you can see the rotation all the way around, right? But notice, what did we say that the red were? The red are the axial, right? So aren't they ultimately going to end up being a little bit closer together than the equatorial? So if you can visualize that and see that, then didn't we just prove why equatorial is more stable than axial overall? Boom. Little MCAT magic, just to get us a couple more questions correct. Yeah, ding, ding, ding is absolutely right. Okay, now let's take this. I love the excitement because this is where it all kind of comes together. This gave me a lot of confidence as a test taker when I was going into this. So watch this. What we're doing now, okay, think back to what we just showed here with the chair. Okay, now watch. This. Boom. I just ring flipped. What the heck am I looking at now? This is crazy. Not actually. Check it out. We're going to move it over a little bit. What you're going to see, this is the boat. Wait a second. Is black carbon? Black's my carbon rings, right? Doesn't this look kind of awkward? I mean, it looks kind of like a boat, but like, what about the spatial arrangement? I'm not loving this anymore. Exactly. It's too close. I'm not loving this anymore. So if we take that, all right? Yeah, it doesn't look good. It's sterically hindered. It doesn't look great even when we bring it together because it's literally too close. So these ring flips are literally showing us the chair. Wait, let me go back one more time. That's the boat, right? If we're looking at the boat, watch what happens. Yep, if you flip a chair, you flip it into a boat. If you flip a boat, you flip it back into the chair. So Laura, this is actually going to prove this. Watch this. Is that a better looking molecule? You bet. You bet it is. That's all it is. What you're literally doing is you're just flipping that ultimate representation. I know, it really is. I love this session on a computer like this. Because you check it out, now I just proved, okay, what I have, the chair conformation, you want to put things in that red equatorial. So what you notice we flipped here, the colors, the idea was the equatorial and the axial literally inverted. Check it out. You can use that to your advantage. So when in doubt on test day, the more stability you're going to have is when you put the largest or bulkiest substituent group into that equatorial position, giving you a more stable molecule overall. So we got to keep going with this. Check this out now. So when I get into it, if I say no, and they can't be interconverted by rotating around a single bond, then what we ultimately end up having is configurational isomers. Now wait a second, where are we going with configurational? That's my third C. So with that configurational isomers, it actually allows it to make it a little, I would say a little bit easier overall to be able to see this. Now we're going to use the hands thing just as quickly, but notice it makes it a little bit easier to work with. So if you see the configurational, if there's a difference in structure, is across a double bond. Okay? Kathy, we'll get there in just a second. Sometimes yes, sometimes no. That's how you ultimately end up proving it. If there isn't a difference in a structure across that double bond, then what we have is optical configurational molecules. So if you get a perfect mirror images that are non-superimposable. Now what I always remember is when we talk about non-superimposable, the question comes up, what does that actually mean? What we have here, all right, perfect mirror images that are non-superimposable. If they are non-superimposable, That, my friends, is the enantiomer. Okay? Exactly. Can you non-superimpose and make my right hand or my left hand fit? Absolutely not. So check it out. We use hands as an example. Right? I can't get those to be exactly the same. Now, let's go one step further with this. Configurational isomers, then, with this chirality aspect. What I have here, okay, are these mirror images of one another? You bet they are. So there's no way, I'm going to rotate this, that they're going to perfectly fit. So if they're non-superimposable mirror images, and they have those 4 different groups, what type of isomer do I have now? Are enantiomers. Very good. See, now this is going to all come together. Let's go one step further with this. I'm going to look at the same thing here. What do I notice is different? I don't have 4 of the same or 4 different groups. So if I don't have 4 different groups, watch this. What is that? If you're superimposable images, is it really even an isomer? No, it's literally just as, I think Kathy was asking this just a second ago, it's the same molecule. There you go. It's a perfect fit. Okay, so we looked at enantiomers, we looked at the same molecule. It makes it a little bit easier because it was only 3 different groups. So you have to have 4 different groups to keep it that non-superimposable mirror image. Now, that's what some of you guys were saying. We could say not chiral or literally achiral overall. So configurational isomers, they're mirror images, which would be non-superimposable upon one another. Okay, so you can look at that in many different conformations, but the idea is to make sure that it fully is. Now, how can this be applied? We're showing you the direct application here. We're not going to go into crazy detail. We just want to see how it is. You have your D-glucose with those chiral compounds. All right. Now, if I were to flip and make this an enantiomer for L-glucose, that means that I have to flip every chiral center. Okay. Now, it's important to show this here because in these chiral carbons, what I want to show you guys now, remember this. I'm going to come back to this in just a second here. The question also oftentimes becomes, I understand what an enantiomer is, but I don't really get what is a diastereomer. Watch. This is my favorite part. If it's not, that's the diastereomer. How can we see this come together now? A diastereomer means, with all those chiral centers we just looked at, check it out. I have D-glucose, but I'm going to show D-mannose, D-galactose, and D-idose. The problem with it is, a diastereomer, you don't flip all of your chiral centers. You just flip at least one, but not all of them. Then we truly have that definition for what a diastereomer is. Does this make better sense now, seeing it visually like this? I think it kind of helps click then. It's not necessarily what an enantiomer is and isn't, but you have to make sure you understand what the diastereomer actually is. So you flip one of them, just not all of them. Okay? Now, meso compounds. I say meso, you say meso, whatever way it is. The only thing a meso compound then is, and this you do not have to go crazy in depth. So I'm actually going to show you guys a couple shortcuts here to make this a little bit easier for you. When you have that, okay, the idea behind it is you have an internal plane of symmetry. All right. Now this you can see here because one's coming out and one's going into the screen. You don't have that internal plane of symmetry. When you have a meso compound, it cancels everything out. So the characteristic you'd be looking for in a passage, it's optically inactive. It's nice, easy information, and it's quick. So what does that mean when I look at something like this? Which one is going to be a meso compound, the one on the left or the one on the right overall? Yeah, the one on the left. So what actually ends up happening, if it has that internal plane of symmetry, it's optically inactive. The one on the right, no internal plane, so it's optically active. Nice, easy points. It's just convention, again. So I'm trying to show you guys the places where we want to have a conceptual understanding and we want to kind of push through, and it's just basic memorization. So we'll see that here. Now, if I look at this real quick, I don't even want you guys to take up a ton of time. Type in the chat right now. 2 molecules depicted below are what? Watch how quickly some of you guys are going to type in. I literally just looked down for maybe 10 seconds. Nope, not mirror images. No internal plane of symmetry. Done. Boom! goes the dynamite. You can call it orgodynamite, you can call that MCAT magic. It doesn't matter because you guys already know I flip one cardinal center, I got diastereomers, I'm moving on. This question, if this is like a discrete question on test day, I'm taking maybe 10 seconds and I'm moving right on. Now, question like number 3 here, this is an example, and I'm not going to go super in depth because you guys will be able to come back to questions like this, so this is a little bit of a tease, but it says how many cardinal carbons are there in morphine? Is this a question you'd want to do right away or potentially skip it and come back to it? I would potentially skip this and come back to it later because what I'm going to have to do is go through and recognize all of my cardinal carbons bonded to 4 different groups, and I got to go through and count each one individually. I would potentially skip this, hold off, and then come back later just because it's going to take me a little bit longer to go through. So think, yeah, big picture and big strategy here. Notice the differences between questions 2 and 3 then. Mark it, come back at the end of the section. Very good, guys. So what we finish up with here is learning goal number 3. Now it's funny because when we get to learning goal number 3, what we're really using here is we're trying to now show how we can use IUPAC nomenclature to show these isomers. Remember R and S configurations, guys? I do because it almost brings tears to my eyes. I thought it was horrible when I first learned it. Check it out. Now we're going to show you guys in a little bit better of a representation how easy this can become. So if we can apply, okay. All right, now if you got it right away, this is great. Let's check it out. I'm looking back. I already brought up this molecule earlier. R2-chlorobutanol. Okay. R2-chlorobutanol. I got it. I got the carbonyl group, aldehyde. Okay. I have my wedges and my dashes, which is giving me a big clue. So let's check it out. I know that I have to assign priority. What do we assign priority, or what is priority determined by? That's a better way to ask that. What's it determined by? Weight. Okay. Now, if you have that, so Crystal, you're not going to make the same mistake again. If you assign it by weight, or the highest atomic weight of the atoms, what happens if you have 2 are the same? Because I know number 1 is going to be chlorine here. Now I have 2 carbons. What do I do if both of them are carbons? This is the part that always used to get tricky. We're going to do a couple of these as we finish up this session here. Not electronegativity, you just go to the next constituent. Yeah, or exactly, the next substituent. So if I do this, my aldehyde group is going to get the second because we have oxygen bonded to it. So then I got 3rd and I got 4th. So what's step 2, guys? I always call it the steering wheel step. Sounds super cheesy, but since it's cheesy, it helped me remember it. Check it out. Step 2, you just draw a circle, or I think it's like a steering wheel. So think about it. If you have 4 there, and I draw it all the way around, I'm going counterclockwise, or I'm turning my steering wheel to the left. To the left is S, to the right is R. But what I see here, now that's step number 3, I have to change R to S or S to R. Do I change this one here? Here, I would, because 4 is not in the back, right? So what ultimately happens is it actually ends up being R. You need to put the 4th substituent in the back. Is it always going to be hydrogen? No. Most of the time, probably. So let's take a little bit closer of a look at this. This is R2-chlorobutanol. So what I can see here, we're going to do another example of this. All right. Notice, what did I just do? It's the same thing we're looking at, right? I'm just going to pull this off. Now watch. I'm just giving a little bit different of a view of this figure. Does that change RS? No, not at all. It's still in the same, remember the C words, configuration. Very good. Okay, so now, what did I just do there? Whoa, 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 whoa. That happened way too quick. Watch. Now I changed something, right? Now I changed. So what happens? Let's assign the same priorities again. Okay, where is the 4th substituent? Is that in the back? Okay, watch. If you rearrange that mentally now, draw a circle. 1, 2, and 3, 4 is in the back. It's clockwise. It's R. So you can do whatever you want, but if you see it that way, yeah, Alexander, it's fantastic. Sometimes it's better to just mentally do it that way You can rotate it, and you can see it then visually. The other way you can think about it is if it's like a steering wheel, that fourth substituent is like the peg of the steering wheel as you turn it. If you can visualize it that way, it all ends up kind of fitting together. So write the name, R2-chlorobutanol, and you're good. So let's take a little bit closer of a look. We said Fisher projections. I like to say Mr. Fisher wore a bow tie. Well, if Mr. Fisher wears that bow tie, what can we do with that? Okay? If Mr. Fisher, and I'm going to say it a couple times because it always helps me remember it, if he's wearing the bow tie, then what happens is everything that's on the horizontal is coming out of the screen or out of the page at you. So how does that help? Well, check it out. I can go through, this is how it's going to be represented, right? With the single lines, not the dashes and the wedges. So we're telling you guys here, if you can visualize it, just like we looked at learning goal number 1, watch how easy this is. We know, just by looking at it, if we want to assign priority. BR is going to get 1, OH is going to get 2, and CH3 is going to get 3. Step 2, okay, this is easy now, isn't it? I don't think this is nearly as bad. Draw the circle. 1, 2, and 3. Where's my fourth substituent according to Fisher projections? Mary is absolutely right. That's a great tip, Mary. It's in the back, so I know if this is counterclockwise or I'm turning my steering wheel to the left. Well, guess what? This just became the priority position of 4 is in the back. I'm good. So what I ultimately can do then, this is S1-bromoethanol. So it literally makes it easier for us to be able to put it in that configuration by having this visualization with a Fisher projection. So you guys are absolutely right. It is easier to determine it when it is a Fisher projection. But the question now becomes, and this is how we're going to finish off this session, because I want to leave this kind of as a way for you guys to think about it. What happens when I get to multiple configurations here? I still have to treat it the same way, right? So let's assign priorities, but understand how those priorities are being assigned. Okay, I have 2 chiral centers here. So we take the first one. If it's 2 chiral centers, we're going to start with this first one right here. This is a type of question. If you got to it on test day, what would you guys do from a strategy perspective? Would you do it right away or would you skip it? Love it. If you guys left here with anything tonight, I love that you guys are all putting skip. You guys got the hour's worth. That is exactly correct. This is going to take you guys a little bit longer. So when I do this, it's not hard to determine the priorities. I have 1 here. I know that that carbon, because it's double bonded to the oxygen, is going to be 2. And the carbon down there is going to be 3 with my 4th. Ooh, wait a second. Is my 4th substituent out of the screen or into the screen? It is a Fisher projection. It's out. So we got to be careful here. I'm going to turn it clockwise R, but since it's in front, I have to reverse. Mr. Fisher wears the bow tie. So it's actually S. Now, let's go one more step with that. If I have 2S3, what this one thing that it does help me do, it does help me eliminate answer choices because the MCAT's multiple choice. So you have a huge advantage as the test taker here. All right? Love it, love it, love it, love it. Now what I would do then, because I've skipped this question, and I'm doing it at the end of this section, and I have a little bit more time, then I'm going back to my second carbon to confirm my answer choice. Well, I know oxygen is going to be 1. I'm going to have the second carbon because it's bonded to an oxygen. The third, wait a second. My 4th H, is that into the screen or out of the screen? Okay, so if I flip it, counterclockwise, 1, 2, and 3, that's in front. So what I theoretically have to do then is flip it again, and it actually becomes R. So the trick to this, but also the advantage to this, is stopping and kind of slowing down. You don't want to do that when you first get to this question. You want to do it at the end of the section when you're not feeling as rushed. I can then apply this information, and it's not as bad. So thereby, because we can really utilize that to our advantage, what we can see is we're literally using that as a way for us to eliminate wrong answer choices and bring it home. Okay? Excellent job. Now, continue to go through. You guys will have certain applications to light rotation, but this is a way for us to determine whether it's optically active or inactive. Remember our racemic mixtures, which we also covered in some of our other science videos, so check that out. Now, that light rotation, if you have that plane polarized light or whatever it may be, you can see where that's all going to come through. So this isn't something that's overly crazy, but the idea is clockwise versus counterclockwise. You're just having different configurations altogether. So that's where you get your D plus or your L minus. Okay? Now, the last step to this then is just simple by convention, and that's your geometric isomers. If there's only two non-H groups across the double bond, where does this ultimately come from? So you have cis and trans, all right, and then E and Z. So the question always becomes, and this is a nice thing to kind of leave here on, what's the difference? The only difference is if you have your non-hydrogen groups on the same side, same rhymes with cis. You're done. Cis is same side, trans just means across. This is simple memorization. This is why we left it to the end of the session. You guys have this no problem. Now the question becomes, okay, well this is pretty easy. What happens when I go from E to Z versus cis and trans? So you guys have a couple questions here that you can help in the end. We're going to sign up for homework for 4 and 5, which is going to make it a little bit easier to bring together. All right, now check this out. This would be a great way to quiz yourself. If I go to no with E and Z, wait a sec. The only thing that's different here is you don't have two non-hydrogens. So just do the highest priority, the same way that we determined R and S. You guys are good to go. E, we just think E opposite. Z, just think same side. So really, is this that bad in terms of what we have to know by convention? Is it really that bad overall? No, not at all. It's a nice quick plug and chug. Now the only thing that you might have then with cyclic compounds, cis or syn is the same side, and then trans or anti. And you guys are set. Okay? So the reason that we put this at the end here, we just want you guys to know there's 2 homework questions that you guys can use as kind of a quick way to review. Okay? But you guys did an excellent job in tonight's session. I want to thank you guys for attending. But remember, organic chemistry isn't that bad. You just bring it all together. You get down the basic conventions. We know the 3 different C values. Boom. You got a little bit of MCAT magic. You can roll it all right together. You guys are going to be able to eliminate more wrong answer choices, be able to choose more correct ones, and you guys are going to turn big areas of opportunity into more points. So I'm going to leave you guys tonight on what I leave every channel session on. Success is when preparation meets opportunity. I'm hoping to see you guys back here soon. Next up, we have Kristen Russell with some thermal chemistry, so stick around, pick up some more info here, and I hope to see you guys back on the channel session soon. Have a great night, guys.